Properties of pure substances. This topic introduces the properties of pure substances as a foundation of thermodynamic analysis. The main focus is how substances with uniform chemical composition can be analyzed in different phase conditions. This discussion becomes the basis for understanding water, refrigerants, and gases in engineering systems. This concept is essential before moving to energy and cycle analysis. The material is closely related to phase change and thermodynamic properties.
Lesson Plan Thermodynamics I. The course structure is arranged progressively from basic concepts to the second law and entropy. This chapter is placed at a very strategic position because it bridges energy concepts and system analysis. Understanding pure substance properties will be used repeatedly in later chapters. This sequence shows that this topic is not isolated, but central to engineering thermodynamics. All advanced applications will depend on these property concepts.
Learning outcome. The learning outcomes emphasize understanding pure substances and phase change processes. Students are expected to read and use PV, TV, and PT diagrams. The ability to use property tables becomes a core skill in solving thermodynamics problems. In addition, the ideal gas concept and compressibility factor are introduced as practical tools. All these objectives build fundamental competence in thermal system analysis.
Nitrogen and gaseous air as pure substances. Nitrogen is considered a pure substance because it has a uniform chemical composition. Gaseous air, although a mixture, is also treated as a pure substance as long as it remains in a single phase. This approach is used to simplify thermodynamic analysis. What matters is not the type of molecules, but the uniformity of composition. This concept is widely applied in engineering practice. Mixtures of liquid and gas phases. Water in a liquid-vapor mixture is still considered a pure substance because the composition is the same. In contrast, a mixture of liquid air and gaseous air is not a pure substance because the composition is different. This classification shows that chemical uniformity, not the number of phases, is the key factor. Two phases can still form a pure substance if the substance is the same. This is a key concept in boiling and condensation analysis. Check your understanding. Number 1. This question emphasizes that water is considered a pure substance because its composition remains constant. Whether in liquid or vapor phase, the substance is still H2O. Phase change does not alter the chemical identity of the substance. This is a fundamental principle in the definition of a pure substance. This concept will be used throughout the entire chapter. Molecular structure of solids. Molecules in a solid remain in fixed positions due to strong intermolecular forces. Their motion is limited to vibrations around equilibrium positions. This structure explains why solids are rigid and maintain their shape. The spring model is used to visualize intermolecular bonding. This concept is important to understand differences between phases. Molecular arrangements in different phases. Transition from solid to gas shows increasing energy and molecular freedom. Intermolecular forces are strongest in solids and almost absent in gases. Liquids lie between these two extremes. This concept helps explain why gas volume changes easily, while solids do not. This is the physical basis of phase change. Water in the compressed liquid phase. At 1 atm and 20 degrees Celsius, water is in the compressed or subcooled liquid state. The temperature is still far below the saturation temperature at that pressure. Adding heat increases the temperature without changing the phase. This condition appears frequently in many engineering applications. The compressed liquid is usually approximated using saturated liquid properties. Water
in the saturated liquid phase. At 1 atmosphere and 100 degrees Celsius, water is in the saturated liquid state. At this condition, the water is exactly at the beginning of boiling. Any additional heat does not increase the temperature, but starts the phase change. This state marks the boundary between compressed liquid and the two-phase region. This point is very important in boiling analysis.
Answer: B. Saturated liquid. Explanation: A. Superheated liquid. This is incorrect because a superheated liquid occurs when the liquid is heated beyond its boiling point at a given pressure, which is not the case at 100 degrees Celsius and 1 atm. B. Saturated liquid. This is the correct answer. At 1 atm and 100 degrees Celsius, water is at its boiling point and exists as a saturated liquid, ready to vaporize with additional heat without temperature increase. C. Subcooled liquid. This is incorrect because a subcooled liquid is below its boiling point and would not be in the phase change condition at 100 degrees Celsius. D. Saturated vapor. This is incorrect because a saturated vapor refers to the state where water is completely vaporized, not in the liquid state at its boiling point.
Saturated liquid-vapor mixture. At this condition, the system consists of a mixture of saturated liquid and saturated vapor. During heating, part of the liquid turns into vapor without any change in temperature and pressure. The proportions of liquid and vapor change gradually during the process. This state is called the two-phase region. Analysis in this region requires the concept of quality. Saturated vapor state. At this point, all the liquid has been converted into saturated vapor. The temperature and pressure remain at the saturation condition during the entire vaporization process. After this point, no liquid remains in the system. This state marks the end of the phase change process. The system is now in a single vapor phase.
Superheated vapor state. After all the liquid has evaporated, any additional heat increases the vapor temperature. The vapor is now in the superheated state. In this condition, the vapor properties begin to resemble those of an ideal gas. No further phase change occurs. The added energy fully increases temperature and internal energy.
TV diagram for water heating at constant pressure. This diagram shows the heating path of water at constant pressure. From the compressed liquid, the temperature rises until it reaches the saturation condition. Then, phase change occurs at constant temperature in the two-phase region. After becoming saturated vapor, further heating produces superheated vapor. This diagram is very important to visualize the boiling process. Saturation pressure of water at various temperatures. Each temperature has a unique saturation pressure value. At 100 degrees Celsius, the saturation pressure is about 101.3 kPa. At higher temperatures, the saturation pressure increases very rapidly. This relationship shows that boiling temperature strongly depends on pressure. Check your understanding. Number 3. This question emphasizes the direct relationship between temperature and saturation pressure. The correct answer is that saturation pressure increases with temperature. This is not a linear relationship, but a strongly non-linear one. This understanding is important for reading property tables and diagrams. Many analysis errors occur when this relationship is ignored. Liquid, vapor, saturation curve for water. This curve shows the relationship between saturation temperature and saturation pressure of water. The curved shape indicates that pressure increases more rapidly at higher temperatures. This curve is also the boundary between liquid and vapor regions.
All points on this curve represent two-phase conditions. This curve is the backbone of phase diagrams. The higher the altitude, the lower the atmospheric pressure. As a result, the boiling temperature of water becomes lower. In mountainous areas, water boils at temperatures far below 100 degrees Celsius. This explains why cooking takes longer at high altitudes. This phenomenon is a direct application of the saturation pressure concept. Liquid N2, maintaining test chamber temperature. Liquid nitrogen exposed to the atmosphere remains at minus 196 degrees Celsius as long as phase change is occurring. As long as liquid is still evaporating, the temperature will not increase. This principle is used to maintain the test chamber at a very low temperature. Insulation reduces heat transfer from the surroundings. This is a practical application of the saturation temperature concept. Temperature and pressure during vacuum cooling. The cooling process starts at about 25 degrees Celsius and atmospheric pressure. When the pressure is reduced using a vacuum pump, the water temperature also decreases. At around 0.61 kilopascals, the temperature reaches 0 degrees Celsius. Cooling occurs because part of the water evaporates and absorbs latent heat. This method is widely used for cooling agricultural products. Answer B. Cooling starts at 25 degrees Celsius and 100 kilopascals, and pressure decreases to 0.61 kilopascals, reducing temperature to 0 degrees Celsius. Explanation. A. Cooling starts at 100 degrees Celsius and ends at 0 degrees Celsius with a pressure increase. This is incorrect because the cooling starts at 25 degrees Celsius, not 100 degrees Celsius, and pressure decreases during the process, not increases. B. Cooling starts at 25 degrees Celsius and 100 kilopascals, and pressure decreases to 0.61 kilopascals, reducing temperature to 0 degrees Celsius. This is the correct answer. It accurately describes the vacuum cooling process, where the pressure drops, leading to a reduction in temperature to 0 degrees Celsius. C. Vacuum cooling increases the temperature to 100 degrees Celsius while reducing pressure to 0.61 kilopascals. This is incorrect because vacuum cooling causes a temperature drop, not an increase, and the temperature drops to 0 degrees Celsius, not 100 degrees Celsius. D. The cooling process starts at 0 degrees Celsius and ends at 25 degrees Celsius with no change in pressure. This is incorrect because the process starts at 25 degrees Celsius and involves a pressure reduction, not no change in pressure. Ice formation via airspace evacuation. By evacuating the air above the water, the vapor pressure is significantly reduced. The water then evaporates rapidly and absorbs heat from the remaining liquid. As a result, the temperature drops to the freezing point and ice starts to form. Insulation prevents heat from entering from the surroundings. This process shows the strong effect of evaporation at low pressure. TV diagram for phase change at constant pressure. This diagram shows the saturated liquid, saturated vapor, and two-phase regions at various pressures. At higher pressures, the difference in specific volume between liquid and vapor becomes smaller. All pressure lines meet at the critical point. Above this point, there is no clear distinction between liquid and vapor. This diagram helps explain the effect of pressure on phase change. Phase behavior around the critical point. The critical point is the condition where liquid and vapor become indistinguishable. At pressures below the critical pressure, phase change occurs clearly. At pressures above the critical pressure, no sharp phase change exists. The substance is in a supercritical state, with properties between liquid and gas. This concept is important in supercritical fluid technology.
Property diagrams of a pure substance. Both the TV and PV diagrams show the same phase boundaries with different axes. Both display the critical point and the saturation lines. The behavior of compressed liquid and superheated vapor can be analyzed from the slopes of the curves. These diagrams make it easier to understand the relationship between pressure, temperature, and specific volume. They complement each other in analysis.
Check your understanding. Number 5. This question emphasizes that at the critical point, liquid and vapor become indistinguishable. There is no longer a clear phase boundary at this condition. The properties of the substance change continuously across this point. This concept often appears in discussions of supercritical fluids. This understanding is important for interpreting phase diagrams. Pressure control in a piston-cylinder device. This system initially is at a pressure of 1 megapascal and a temperature of 150 degrees Celsius. The pressure can be reduced by decreasing the weight on top of the piston. During this process, heat can be added to control the thermal condition. This example shows how pressure and volume can be mechanically controlled. The piston-cylinder device is a fundamental model in thermodynamics. PV diagrams of different substances. This diagram shows the solid, liquid, and vapor regions together with their boundaries. The triple line indicates the condition where three phases coexist. The critical point marks the upper limit of separate liquid and vapor phases. The shape of the diagram differs depending on whether the substance expands or contracts on freezing. This confirms that phase behavior strongly depends on the nature of the substance. Triple point of a substance. The triple point is a unique condition where solid, liquid, and vapor coexist in equilibrium. Each substance has its own specific triple point. This condition occurs at one specific combination of pressure and temperature. Outside this point, only two phases or a single phase can exist. The triple point is often used as a reference in temperature calibration.
Answer: A. The substance exists simultaneously as solid, liquid, and vapor at specific temperature and pressure. Explanation: A. The substance exists simultaneously as solid, liquid, and vapor at specific temperature and pressure. This is the correct answer. The triple point condition is a unique state where a substance can exist in all three phases, solid, liquid, and vapor, at a specific temperature and pressure. B. The triple point condition occurs at a random point on the phase diagram, unrelated to temperature and pressure. This is incorrect because the triple point condition occurs at a specific fixed temperature and pressure for each substance. C. At the triple point condition, only two phases coexist in equilibrium. This is incorrect because the triple point condition involves all three phases, solid, liquid, and vapor in equilibrium, not just two. D. The triple point condition is only applicable to gases, not liquids or solids. This is incorrect because the triple point condition applies to all phases of matter, solid, liquid, and vapor, not just gases. Triple point properties of various substances. This table shows that each substance has a different triple point value. Water has its triple point at 273.16 Kelvin and 0.61 kilopascals, while CO2 has it at very different conditions. These differences reflect the molecular nature of each substance. The triple point is a fundamental property of a substance. Such data are important in scientific and high-precision engineering applications. Sublimation of solids at low pressure. At pressures below the triple point, a solid cannot melt. The solid changes directly into vapor through sublimation. The most common example is dry ice or solid CO2. At atmospheric pressure, CO2 never becomes liquid. This phenomenon shows the important role of pressure in phase change.
Phase diagram of a pure substance. This diagram summarizes all regions of solid, liquid, and vapor phases. The triple point and the critical point are the two main landmarks of the diagram. The sublimation, melting, and vaporization lines separate each region. Phase change paths can be clearly traced on this diagram. This diagram is a complete map of the thermodynamic behavior of a pure substance. PVT surface of a contracting substance. The PVT surface shows the three-dimensional relationship between pressure, specific volume, and temperature. The solid, liquid, and vapor regions form connected surfaces. The triple line is where the three surfaces meet. The critical point marks the end of the liquid-vapor boundary. This visualization helps to understand phase behavior in a comprehensive way.
Check your understanding. Number 7. This question emphasizes that the critical point is the end of the liquid-vapor boundary. Beyond this point, there is no clear distinction between liquid and vapor. The properties of the substance change continuously across this condition. This concept is important for understanding supercritical fluids. Many modern applications use conditions near the critical point. PVT surface of a substance expanding on freezing. For substances like water, the solid region has a larger specific volume than the liquid region. This is clearly visible in the shape of the PVT surface. This behavior explains why ice floats and why pipes can burst when water freezes. Although the shape is different, the basic structure of the diagram remains the same. This shows how the unique properties of water arise from its phase behavior. Analysis of control volumes. A control volume is an open system where mass and energy can cross the system boundary. At the inlet and outlet, the specific energy is expressed in terms of U, P, and V. The combination U plus PV represents internal energy and flow work. This concept is the basis for analyzing flow systems such as turbines and pumps. Without this understanding, energy balance for open systems cannot be performed. Pressure-volume product as energy units. The product of pressure and volume has units of energy. In the SI system, 1 kilopascal meters cubed is equal to 1 kilojoule. This shows that boundary work and flow work can be directly expressed in energy units. This conversion is very frequently used in thermodynamic calculations. Understanding this unit relation prevents dimensional errors in calculations. Saturation properties of water. This table presents the saturation pressure and the specific volumes of saturated liquid and saturated vapor. For each temperature, there is one corresponding saturation pressure. These data are used to determine properties at saturated conditions. This table is the main tool for solving phase change problems. Almost all steam system calculations depend on this table. Quality of saturated mixture. Quality represents the mass fraction of vapor in a two-phase mixture. A value of x equals 0 means the mixture is all liquid, and x equals 1 means it is all vapor. For intermediate values, the system is a mixture of liquid and vapor. This concept is very important to calculate the average properties of the mixture. Without quality, analysis of the two-phase region cannot be done. Answer B. Quality represents the ratio of vapor mass to total mass in a saturated mixture, defining phase proportions. Explanation. A. Quality represents the ratio of liquid mass to total mass in a saturated mixture. This is incorrect because quality refers to the ratio of vapor mass, not liquid mass, in a saturated mixture. B. Quality represents the ratio of vapor mass to total mass in a saturated mixture. This is the correct answer. The quality, X, of a saturated mixture is the ratio of the vapor mass to the total mass, defining the proportion of vapor in the mixture. C. Quality is only relevant to superheated vapor and not to saturated mixtures. This is incorrect because quality specifically applies to saturated mixtures, not superheated vapor. D. Quality indicates the ratio of heat absorbed to heat rejected in a saturated mixture. This is incorrect because quality is related to phase proportions, liquid and vapor mass, not heat absorption or rejection. Homogeneous mixture in two-phase systems. Although it consists of two phases, the mixture is often treated as a single homogeneous system. Average properties, such as specific volume, can be calculated from the contribution of each phase. This approach greatly simplifies the analysis. Physically, the phases are separate, but in calculations, they are treated as one. This is a standard technique in engineering thermodynamics. Quality on PV and TV diagrams. Quality can be visualized as a relative position between the saturated liquid and saturated vapor lines. The relation V equals VF plus XVFG shows how specific volume changes with quality. The larger the value of X, the closer the state is to saturated vapor. The diagram helps to understand the geometric meaning of quality. This makes interpretation of calculation results easier. Specific volume in saturated mixture. The specific volume of a two-phase mixture always lies between VF and VG. This value is determined by the system pressure or temperature. If V is known, the quality can be determined. This relation is the basis for many steam property problems. It shows that V is a strong indicator of phase condition. Approximations for compressed liquid. For compressed liquids, properties are often approximated using saturated liquid values at the same temperature. This approximation is sufficiently accurate for many engineering applications. Specific volume, internal energy, and enthalpy can be taken from saturated tables. This saves time and simplifies calculations. The resulting error is usually very small. Compressed liquid condition. A substance is in the compressed liquid state if its temperature is lower than the saturation temperature at that pressure. The example at 500 kilopascals and 75 degrees Celsius shows this condition. Since complete tables are not always available, the saturated liquid approximation is often used. This is a common practice in engineering calculations. Understanding this condition is important to choose the correct property data. Check your understanding, number 9. This question reinforces that a substance is considered a compressed liquid when its temperature is below the saturation temperature at that pressure. If the temperature is lower than Tsat at P, the substance must still be in the liquid phase. This concept helps avoid mistakes in choosing the correct property tables. Many errors occur due to wrong phase identification. This understanding is fundamental in property analysis. The ideal gas equation of state relates pressure, specific volume, and temperature. Many real gases can be treated as ideal gases at low pressures. The value of R shows the differences between gases. This equation is very important in gas system analysis. Properties per unit mass and mole. In thermodynamics, properties can be expressed per unit mass or per unit mole. A bar over the symbol indicates a per mole basis. The choice of basis depends on the type of analysis being performed. In mechanical engineering, the per mass basis is more commonly used. Unit consistency is very important in calculations. Ideal gas assumption and error. Not all conditions can be treated as ideal gas without error. At high pressures, deviations from ideal gas behavior become significant. At large specific volumes and low pressures, the ideal gas assumption becomes more accurate. This chart shows the region where the error is less than 1%. Understanding this limit is important for choosing the right model. Compressibility factor Z. The compressibility factor Z is used to measure the deviation of a real gas from ideal gas behavior. For an ideal gas, Z equals 1. For real gases, Z can be greater or less than 1, depending on the condition. This deviation is caused by intermolecular forces and finite molecular size. This concept corrects the ideal gas equation for real conditions.
Answer: C. The compressibility factor Z for ideal gases is 1, and real gases deviate from this value due to intermolecular forces and finite molecular size. Explanation: A. Z is always equal to 1 for real gases, regardless of pressure and temperature. This is incorrect because Z for real gases can vary and is not always equal to 1. It can be greater than or less than 1, depending on the conditions. B. Real gases always have a compressibility factor greater than 1 due to intermolecular forces. This is incorrect because real gases can have Z greater than 1, but it can also be less than 1, depending on the specific conditions, not always greater. C. The compressibility factor Z for ideal gases is 1, and real gases deviate from this value due to intermolecular forces and finite molecular size. This is the correct answer. For ideal gases, Z equals 1, and real gases deviate from this value due to intermolecular forces and finite molecular size. D. Real gases behave exactly like ideal gases at all pressures and temperatures. This is incorrect because real gases only behave like ideal gases at certain conditions, low pressure and high temperature. At other conditions, real gases deviate from ideal behavior. Comparison of Z factors for various gases. This chart shows how Z varies with reduced pressure and reduced temperature. Each gas has a different curve but follows a general trend. At high reduced temperature and low reduced pressure, Z approaches 1. This indicates behavior close to an ideal gas. This chart is used to estimate Z in practical calculations. Transition to ideal gas behavior. All real gases behave like ideal gases at very low pressures. Under these conditions, the effect of intermolecular forces becomes very small. Therefore, the ideal gas equation becomes increasingly accurate. This is true for almost all temperatures. This concept explains why the ideal gas model is often the first approximation in analysis. The largest deviations from ideal gas behavior occur near the critical point. In this region, the gas shows strongly non-ideal behavior. At low pressures and high temperatures, gas behavior approaches ideal again. This diagram helps determine when the ideal gas model should not be used. This is important in high-pressure system design. Determining compressibility factor. The compressibility factor can be determined using reduced properties and correlation charts. Pressure and volume or temperature are normalized by critical values. This approach allows one chart to be used for many gases. This method is very useful when experimental data are limited. This is a standard technique in engineering thermodynamics. Check your understanding. 11. This question emphasizes that reduced properties are used as inputs to estimate real gas behavior. These properties are expressed as ratios to their critical values. With this approach, many gases can be analyzed using a single set of generalized charts. This concept greatly simplifies real gas analysis. This is the basis of using compressibility factor charts. Accuracy of compressibility chart results. This chart compares the exact pressure values with results from the Z-chart and the ideal gas assumption. The Z-chart result is very close to the exact value. In contrast, the ideal gas assumption can give large errors under certain conditions. This shows the importance of non-ideal corrections. The choice of model strongly affects calculation accuracy. Historical equations of state.
Many equations of state have been developed to model real gas behavior. Van der Waals is one of the earliest and simplest. Other models, such as Redlich-Kwong and Benedict-Webb-Rubin, are more accurate. The main goal of all these models is to predict real gas properties. The complexity of the models increases with the demand for accuracy. Critical isotherm of a pure substance. The critical isotherm is the curve at the critical temperature. At the critical point, this curve has an inflection point and shows no phase change. Above the critical temperature, condensation is no longer possible by increasing pressure alone. This shows the physical limit between liquid and gas behavior. This concept is important for understanding supercritical transitions. Accuracy of complex equations of state. The more complex the equation of state, the higher the accuracy that can be achieved. Van der Waals has the lowest accuracy and a limited range of applicability. Models such as Beatty-Bridgman and Benedict-Webb-Rubin are more accurate at higher densities. Virial and Strobridge models are well suited for numerical calculations. The choice of model must match the required accuracy. Error analysis of equations of state for nitrogen. Van der Waals shows the largest errors, especially at low pressures. Beatty-Bridgman gives better results in the mid-range. Benedict-Webb-Rubin shows the smallest errors under almost all conditions. This confirms the importance of choosing the right model. Answer: C. Benedict-Webb-Rubin. Explanation: A. Van der Waals. This is incorrect because the Van der Waals equation has the highest errors, especially at low pressures, making it less accurate compared to other equations. B. Beatty-Bridgman. This is incorrect because the Beatty-Bridgman equation offers moderate accuracy, particularly for mid-range pressures, but not the lowest errors across all conditions. C. Benedict-Webb-Rubin. This is the correct answer. The Benedict-Webb-Rubin equation provides the lowest errors across a wide range of conditions, making it the most accurate in various scenarios. D. Ideal gas law. This is incorrect because the ideal gas law is an approximation that is only accurate under low pressure and high temperature, and it does not account for intermolecular forces or volume exclusions like the other equations. References. This slide lists the main source of figures and material, which is the book by Chengel and Bowles. This reference is one of the international standard textbooks in engineering thermodynamics. Using credible sources ensures the accuracy of the material. Students are encouraged to refer directly to this book for deeper study. This confirms that the lecture material is based on strong literature.